Hello everybody! Today we are going to look at an example which is often called Hutton's razor after Graham Hutton and Ockham, who had a saying that you should always keep things as simple as possible. So let's get into it. So this is an example of a small programming language, a very small programming language, hence the razor. Where we have numbers, we have booleans, we have addition of implicitly numbers, but here we are saying expressions for now, and we have an if then else, where again we're assuming that this first expression is really a boolean, right? So here are some example expressions: 7 plus 3 plus 5, and here's an if plus 0, and here's an if where we don't have a boolean in the test position, so that's probably not going to be very well. And if we want, we can evaluate these things, Control C, Control N, E1, but it's not actually going to do anything, right? Because these are just pieces of syntax built up from these constructors, so there's nothing to really normalize. If we want to evaluate them, we have to write our own evaluation function, and that's what we want to try to do. So we want to write an eval, which takes an expression and then gives us back some kind of value, right? So because we have two kinds of basic things, we have numbers and bits, we can't just write a single type here, so we have to define our own type of values, which includes these two things, right? So I'm going to say that a value is a set, and I have two constructors. I have a way to include the natural numbers into values, and I have a way to include booleans into values, right? Okay, so then I can choose which one of these I want to use depending on what basic value I have here. Okay, so let's see if we can do this. So we pattern match on the E. Okay, and let me do the usual renaming. I like to call my numbers N and my booleans B. And I like E prime. Okay, so some of these are easy, right? If I evaluate a number, then I just get that number back. And if I evaluate a bit, I just get that bit back. And here, what we would like to do is we would like to evaluate E. It's going to be a value. And then we would like to add that to what we get if we evaluate E prime, right? But we see that this doesn't make sense because addition is defined on natural numbers, not on values. So we could try to define our own version of addition on values. Val to val. Okay. And if we do this, we have to pattern match on V and V prime. And we see if they are both numbers, then that's fine. Then we just return their sum. Reload first. But if you're trying to add a number and a bit, then this really doesn't make any sense, right? This should be a type error because we're trying to add things of different types. So actually, we can't always produce a value here. So typical way to do this is to use the maybe type instead. Right? In which case I have to say that this is just the result I want. And all these other ones are going to be nothing. So I'm just going to do a catch all for the rest of them. Like that. Okay, but if this is returning a maybe type, then I have to make this whole thing return a maybe type, right? Which means that these has to be just. Like that. And here I can't just evaluate directly like this anymore, right? I have to do this in the maybe type, and then I have to see if I got the result out or not. And if I did, then I can continue. If I got nothing, then the whole thing should be nothing, because then I failed, right? So you might remember this from Haskell, that we can do this with do notation. So we can do that also in Agda. And the reason we can do that is that I've imported data maybe, which defines the combinators for bind for the maybe type. So let's do this with do. So the first thing we want to do is we want to evaluate E, and we're going to get a V out. Okay, and then we'll evaluate E prime, and then here we are going to return V plus value V prime. Right. Okay, so if any of these fails, then the whole thing is going to return a nothing because of the way bind is implemented for maybe. But we can also read this rather operationally. I do this, then do that, and then return this. Right? And this is doing the just in here. And in the same, okay. So here we have to do the same thing for the if then else, right? So I'm going to start with the do. And the first thing I'm going to do is I'm going to try to evaluate the test expression. But here I'm only happy if this is a boolean, right? So you can actually do this in either, you can pattern match in your do block. So I'm saying that, well, I want this to be a bit. If I try to load this, then here I get an error about incomplete pattern matches because we don't know that this is actually going to be a bit, right? So you see that the missing case is if it's a number, because these are the two values it could be. So in order to deal with the rest of the cases, we can say where underscore goes to, and then here we give something, and here we just want to fail if it's something else, right? So here in general we get all the other cases, and sometimes you might actually want to do something with this x, but here I don't care. I'm just going to say, well, if it's not a bit, then fail. Okay, so now we know that it is a bit, so we can say that if b something, if b then something else something, and then here we can just evaluate e prime, and here we can evaluate e double prime. Right. So in particular, note that we are only evaluating these branches if you're in the right branch. So we're not, if these had side effects, then it wouldn't be okay to evaluate both of them and then choose between the results. But we're doing this inside the branch. Okay, so let's see if we can run some tests. So if we evaluate E1, which we had up here, then we should get 15, right? So that's a just, it's not going to fail, and it's a number 15. And claiming that this happens by computation, so this is just REFL. Okay, and that type checks, so that's okay. Let's do the same with E2. If we evaluate E2, then we get just of something, and claiming that this is by REFL. And now if I fully normalize the solving, so Control U, Control U, Control C, Control S, then Agda is going to solve this for me. And because I said that the proof was REFL, then it's just going to find the thing that this evaluates to. So see that it's 2 in this case. If true, then 2 plus 0. Yeah. Okay, and if you try to evaluate this last one, which wasn't type correct, so it's an E3. If you do the same thing, we're saying it's just something, the proof is REFL, then here we see that REFL doesn't work because nothing is not just something. So this actually fails and we get the nothing here. Okay, so what have we learned? Well, we can use data to represent expressions like we did here and also here for the values. We can use pattern matching to evaluate these expressions like we did here. And we use the maybe monad to make sense of this risk of failure. And so far we could have done all of this in Haskell. Right? There's nothing dependently going on here except for these tests, which we could have done differently in Haskell. But we do have this nice syntax for pattern matching in a do block where you can say in all other cases do something like this, which you can't do in Haskell. And the use of this maybe monad makes life harder because we always have to deal with these things. Since particularly if you want to prove something about this, then it's quite hairy to always have a maybes. You always have to deal with the case where it fails and the case where it doesn't fail, etc. And it gets old quite soon. So let's see in future videos if we can make something about this and make our life easier.